So today, we are going to talk about transformers. Okay? Well, what is a transformer? Okay? One of the things that we can talk about, actually leading up to that, is something called electromagnetic induction. So we kind of actually did a little bit, we go way back to electrostatic. We can understand that electric charges create an electrostatic field around them, okay? Electric force field around them. And when we put that near items that have the capacity for magnetism based off of what they are made out of, we can actually blend the worlds of an electric field and a magnetic field. And that electromagnetic field can do some things for us. So we're starting here, and I'm actually noting on your note sheet about halfway down. Like there was stuff that preceded this when I used to do this as a full unit. We introduced the concept of what's called electromagnetic induction. Basically, that electromagnetic field can cause changes in other things that also have electromagnetic properties. And specifically, talk about transformers. What they do is it's a device that basically can just change, modify the voltage in an alternating current situation. Now, alternating current. This is very different than what we spent a lot of time talking about previously, because everything that in circuits we did earlier was what? Direct current. Okay, battery-powered things, that currents all flow in one direction. Now, we use kind of this electromagnetic field to our advantage when we start to create these transformers. But I need you to understand that the transformers, they don't work in battery-powered circuits. Okay? They do work in alternating current circuits. And what we do, depending on how we use it, we use them to either increase or decrease the AC voltage that is being used. Now, in our house, hopefully you remember this way back to the beginning of circuits, but everything that you plug into the wall gets very close to 120 volts. Okay? It's not perfect, but it gets very close to that. But here's the thing. Do you think that most devices that we use 120 volts? No. You plug in your phone into the wall. Are you using 120 volts from the wall? Like all the way to your phone? No. Okay? The little cubes that you use, what do? They're going to convert that to a usable form in the amounts and things that you would want for those devices. And here's the thing. Like I said, most things use between 3 and 9 volts. It's just that to get that energy that comes from eventually where our power source is to our devices, we have to use a combination of step up and step down. So let's just think about this for a second. Do you know where we get most of our power here in Northern Virginia? Where does it come from? Where do we get the power plant that gives us most of our energy? There is. So there is a lot there, but actually here in Northern Virginia, it's a little bit different than where we get most of our power. There's some hydroelectric, but that is more towards like Central Virginia as to where that is delivering power. We actually get a lot of our power from Lake Anna Power Station. Lake Anna Power Station. Oh, okay. It uses a fun little source of energy. But with Lake Anna, okay, think about that. Think about the distance we are. If you know where Lake Anna is, okay, without traffic, you're talking about an hour and a half, 45-minute drive. Memorial Day weekend, a lot more. Okay, but that thing about how far away that is, and we have to get the power from there to, let's just say, your house, and obviously lots of other houses as well. Okay, but the power has to get there. Well, the power that is created at that power station, okay, we need to step up the voltage in order to efficiently transmit that on power lines to go from Lake Anna, even here to just Loudoun County. Okay? So yes, there are very high voltage power lines to do that. Well, how do we step up that voltage? With very large transformers that we use to then step that up. That sends it over great distances very efficiently. Then, do you need 20,000 volts going into your home? So what do we have in your neighborhood? What do we have at different, power stations around it? We take from those super high power lines, super high voltage lines, and then step down. And you have the big transformers, the green boxes that are, now some of them are like for cable TV and other things, there's not all of them. But yeah, those that maybe resemble about the size of your desk. Okay, a lot of those are step down transformers in your neighborhood to go ahead and bring that down to 120 volts. And I'm sure you've been around, you've lived anywhere long enough, like sometimes those transformers blow, like they got to be maintained or fixed in order to kind of keep doing what it is that they do. But those step down transformers, again, step it down so that's a reasonable quantity, and then all the devices you plug into your outlets step down in the devices themselves. Go ahead and get that to the appropriate amount. So picture tube, we don't do a whole lot of picture tubes anymore, but picture tubes in TV need about 15,000 volts to accelerate the electron beam that it uses. And obviously a transformer is used in that one to step it up. So there still are devices that use higher voltage. Now, I know that you are probably conditionalized to think, oh, super high voltage, everything's dangerous. No, we actually have some things that are very high voltage and super low currents that still are safe. It's just a combination of those two, and often when that current gets to be a bit higher, that's when we need to be concerned. Okay? Now, yeah, it does. Okay. But what is a transformer? Okay? It consists of an iron core in which we have two coils of wire that are wound. It's worth noting, kind of see down here, I'll get to the picture in a second, that the wires themselves do not actually connect with each other, they don't touch. They are wrapped around different sides of this iron core, and the electromagnetic field that's around it induces that change that we're going to talk about here in a second. So the first coil of wires on one side we just call the primary coil with, number of turns is why N is used for this. With P as subscript, that's our primary coil side. Think primary, first, think like that's where it's coming from. Okay? The secondary coil is going to be the other side of it. That's going to be the sending side of that, so NS. And the equation to figure out whether something is going to be a step up or a step down transformer is going to be as we see it here. Okay, so NS over ND is how I start with things. So the number of turns, or the number of coils on the secondary side, number of coils on the primary side, that is a ratio. And that helps us to determine then what's going to happen to the voltage. Okay, are we stepping it up? Are we stepping it down? Now, it would be completely useless, but what if we had the same number of coils on both sides? And what would happen? One. It wouldn't really change anything about it. Okay, so the number of coils that we have on the different sides, and you should know, like, look, it's usually more than two, okay? But often the number of coils that we have, again, that helps to figure out what's going on. One thing about it, though, is that, I guess we'll get to this on the next slide. Okay, according to the transformer equation, if the number of coils on the secondary side is greater than the primary, the secondary, or the output voltage, is going to be greater than the primary. Okay, so it steps up the voltage. Fantastic. If NS, or the number of turns on the secondary side, is less than NP, the number of coils on the primary side, the output voltage is going to be less than the primary voltage, and this is a step-down transformer. You know what, to kind of make another parallel to this, have any of you done international travel where the plugs are different in different locations? Okay, what do you have to do in those places? You usually bring with you a little mini transformer set. Okay, so that you have stuff that is rated for 120 volts. But what if you're plugging into something that is 100, or depending on what different countries are. Some countries want to change that. They have higher ones at 220. And what do we have to do with that? Okay, we step it up or we step it down. Okay. Now, there's one thing about that though. Sure, we can step it up, we can step it down, we can change what that voltage is going to be. Most transformers are very efficient, but the byproduct of the inefficiencies of it is always going to be in the form of heat. Okay, so often, these transformers, they can get warm, but that is, depending on how it's designed, that's just going to be the byproduct of what we have. Usually, at least 99% of the energy going in is just transformed to something else. It's not a loss of energy. So So we can go ahead and get there. Now, assuming though that the energy transfer is 100%, and we're going to start with that. We're not going to talk about the inefficiencies of it. That the power delivered to the primary coil is equal to the power delivered to the secondary coil. Hold on a second. Think about that. Assuming it's 100% efficient, which it is very, very close to, power in equals power out. But let's just say it's a step-up transformer. If the voltage is going up, what has to change? Okay? So as we step up the voltage, the current is going to drop, or vice versa. Okay? If we drop the voltage, then the current is going to go up. Okay? So the power itself remains the same. So one thing I want you to notice, because you can technically tie all of this together if you wanted to, notice how in terms of the number of coils for primary and secondary, they match voltage. Okay, secondary is up top, secondary is top, primary on bottom. Okay, but in terms of the current, the ratio is flipped. Okay, because it is an inverse relationship with the current itself. Question?
Oh, I was wondering about, is the reason why if you look at the transformer, it's a bunch of plates that are glued together, is that to increase efficiency of that one big metal block?
It depends on what the transformer is rated to deal with. Because you may have some that are dealing with, if you're trying to talk about that, what you design in a neighborhood and to distribute that, it's going to physically look different than what you would have if you were to break down, transformers within appliances. It's just what they're rated to handle and how they're going to deal with it. So the overall capacity of what they do. So as we said, a step-up transformer steps up the voltage, but simultaneously steps down the current. Transformer that steps down steps up the current. Okay, but the power remains the same across the transformer. Cool. We're going to do one sample problem together. Sound good? I think. Do I have this in your notes? Okay, so here's what we're going to do. On your practice problem set that you have, let's just make some space there underneath number 5, leave some room, and we'll do sample problem A. So a step-down transformer inside a stereo receiver has 330 turns primary, 25 in secondary. Plug connects to the coil, which is a 120-volt wall socket, which means where is this located? In the United States of America, or some other place in North America that's going to be close to that. Okay, and it has a current of 0.83 amps. We're going to find some things. So the first thing we're going to find is the voltage across the secondary coil. So what are we trying to find here? Vs. Okay, and even if we have to go back and take a look at this, okay, so Vs equals this ratio. What are we going to do to get Vs by itself when we have the number of coils? We're going to multiply both sides by Vp. So here's what I'm going to do. That's going to be equal to Vp times the ratio of Ns over Np. Ladies and gentlemen, I think you're going to find this is not exactly rocket science in terms of the calculations. So let's go ahead, let's do our substitution, and let's figure out what we have. Okay, our primary voltage that we were given here is 120 volts. All times the number of coils in the secondary coil, which is going to be 25, over primary, which is going to be 330. And as you can see, we're multiplying it by a ratio that is going to greatly reduce this. So 120 times 25 over 330. Lucas, you seem like you got a calculator ready to go. What do we get? 9.091 monkeys, bananas, gallons of milk, volts, good. Okay, 9.091 volts. Cool. Questions? Pretty easy stuff, right? Okay, so we're stepping 120 volts down to a little bit more than 9 volts to go ahead and use within that. Okay, the current within the secondary coil. Okay. Well, we could do this a number of different ways, okay? But let's do this. Okay, let's actually start off with the ratio IP over IS. So, and that is going to be equal to NS, I would write it that way, over NP. So how are we going to go ahead and rearrange this so that we get IS? What would you do? I would do the same thing. All right, let's just flip the whole thing. Again, if we flip both sides, what we do to one side, we do to the other, which will give us IS over IP equals NP over NS. So let's go ahead, let's flip this part of it. So that would be NP over NS. And then what are we going to be multiplying that by? IP. They are current in that. And that is going to be equal to IS. Oh, good. Okay, because we have the primary current here. So 0.83 amps. And that is all going to be multiplied by the 330 over 25. And you got it? Let me know. 10.96 amps. Ladies and gentlemen, do we agree with that? Go to 3 decimal places. No, all right, good. Let's do that. 9. You said 956. Good. 956 amps. Now do we agree? Yeah. Okay. Cool. So we can see this. We've taken our 120 volts and we've now reduced that to a little more than 9 volts. But look at our current. We went through less than 1 amp, and now we've stepped that up to almost 11 amps. Okay, so definitely seeing that transformation. All right. The average electrical power delivered to the rest of the stereo. Now, we actually have 2 different ways we can find this. And I'd actually like to, just for kicks and giggles, I'd actually like to solve for it both ways. Okay? But let's do it this way. Let's say the power based off the secondary coil, which would be Vs and Is, which we actually just solved for, which would be our 9.091 times our 10.956. Let's go ahead, pluggy chuggy. Let's see what we get. You got it already?
99.601 watts.
Hold on, one more time, a little slower.
99.601 watts.
99.601 watts. Cool. So just less than 100 watts for that. But I'm just curious. Again, humor me here. What if we were to do this based off our primary values? Okay, so VP times IP, there we go. So our voltage primary, we're told, well, that one was our 120 volts. And then we know that our primary current was given to us as 0.83. What do we get when we multiply them together? 99.6 watts. Now again, yes, I would attribute this to, we did truncate that or round that to the thousandths place with our values in the secondary coil of what we found. But just to make the point, the power effectively remains the same. Okay? All we're doing is kind of a trade-off then between the voltage and current within the transformer. Sound good?